So for those of you that are taking the grade 12 pre-calculus, this is a section that is also found in that course. So if you can hammer it out and apply it, it'll make it a lot easier when you get to pre-calculus. We're looking at counting principles. So the fundamental accounting principle says the following. If one task can be performed in A ways and another task can be performed in B ways, then both tasks can be performed in A times B ways. The series of tasks can be performed in A ways and B ways and C ways and so on. All these tasks can be performed in A times B times C ways. For OR situations, the fundamental accounting principle does not apply. If the tasks are mutually exclusive, they involve disjoint sets, A and B, so the number of A union B is equal to the number of A and the number of B. The set tasks are not mutually exclusive, they involve non-disjoint sets, C and D. Number of C union D is equal to C plus D minus C and D, the principle of inclusion and exclusion. Outcome tables, organized lists, and tree diagrams are useful to help solve counting problems when you need to display all the possible outcomes. Okay, so let me explain this again. In the last section, when we looked at A union B, okay, we took all of that was in A, we added it to all that was in B, and then we subtracted the one that was in both of them, correct? Remember this, right? Okay, so this is called the principle of inclusion. Now, if this set was disjoint, meaning that they didn't have anything right here, then what does that leave us with? All of A or all of B, and that's it. Okay, so that's all of those two sets. So if the set was called if it was said that they were disjoint sets, they had nothing in common, this wouldn't be here. That value would actually be 0. All right? Now we're going to call that mutually exclusive. So disjoint set and mutually exclusive mean the same thing. There is nothing in common in set A or set B. Fair enough? So this is how we've already done this. This relates to what we've already done. Okay? Now, we're also going to use tree diagrams. For those of you that take the pre-calculus class, the tree diagram is the easiest way in which we do these problems. Okay? They're not as difficult when they ask you to do a simple task, but when they ask you what the probabilities are, the tree diagrams become a little more complicated. So what we're going to do is we're going to hammer out what a tree diagram looks like, and basically we're just going to count it. All right? That's the easiest way to do these questions. So let's look at the first example in this. Kim is choosing a new cell phone. She can choose between the 300, the 400, or the 500 model in green, pink, indigo, orange, or taupe. Kim is also deciding whether or not to get a data plan for her phone. How many different choices does Kim have altogether, accounting for model, color, and data plan, or not? Okay. So she has a number of decisions to make. I'm going to show you two very specific ways in which we can organize this. I'm going to show you the quick and easy way, which is going to be set up for all of them. And then I'm going to show you the way in which we set it up with a tree diagram. We just simply count it out. For each decision you have to make, I place a blank. This is actually 4.2. So in 4.2, we learned about the fundamental counting principle. And this is what the fundamental counting principle looks like. So she has to choose, first of all, a model. So I place a blank. How many choices does she have for that model? 3 choices. Then she has to choose a color. How many choices of colors does she have?
5.
5 choices of colors. And then she has to choose whether or not she wants a data plan. So she has a choice of getting a data plan or not getting a data plan. So how many choices does she have here? 2. So the total number of ways in which she can select a model, a color, and whether or not she has a data plan, I multiply these together. So there's 30 ways in which we can do that. That's pretty straightforward. Each blank represents a decision to be made. Okay? And inside the blanks goes the number of options you have for that decision. Fair enough? Now, if you look at the top of page 91, it draws it out in a tree diagram. You can do this in a tree diagram as well. So they set up the models, right? And then they did the colors. So there are 5 of them, right? So 5 colors for each. And then whether or not you had a data plan. So yes, no, basically. All the way down. And then they counted, and then if you just counted them, how many would you have? So go down, you count them, you'd have 30 different ways in which we could choose this. So that's very straightforward. Each blank in a fundamental counting principle represents a decision, and inside each blank represents an option that you have. Okay? Now, the problem with on the top, the tree diagram on 91, it's for part B, not for part A.
I was like, that's not right.
Right. So part B says this. The store agent advises Kim not to choose the 300 model if she wants a data plan. Also, the 500 model is not available in indigo or taupe trim. How many choices does Kim have now? All right. Now, the fundamental counting principle can be used for this. You can now look at it and you can use what we call restrictions on it and draw those out first and then make a decision. So that's one way to do it. I'm going to show it to you. The easier way is the tree diagram for this particular question. But I'm going to show you how we would actually approach this. All right. So it says here that the store agent advises Kim not to choose the 300 model if she wants a data plan. So I'm going to very specifically say I want a data plan. That's my restriction on it. That's my first restriction. There's actually 2 restrictions. The first one is she wants a data plan. So how many choices do I have right here if she wants the data plan? I only have 1 choice, right? Now when I look at the models, how many choices does she have for the models if she's choosing a data plan? 2. 400 to 500. Correct? And how many choices does she have for color now? 5. She still has 5 choices for color. So if she wants the data plan, there's only 10 choices she has now. Correct? Okay. Store agent says, advises Kim not to choose the 300 model if she wants a data plan. Also, the 500 model is not available in 2 of the colors. How many choices does Kim have now? So if I look specifically at the 500, okay, that's exactly correct. So I have 2 cases that I can also look at. The first case is if she wants a 500 or if she wants a 400. So if she chooses the 400, I have 1 choice right here, right? Because it's going to be the 400. It also says that I've got a data plan. So I have 1 choice right there.
2, 4, 6, 5.
Yeah, you can have a data plan or not a data plan.
Ah, okay, that's right. So I do have a choice here, don't I? I have 2 here. Right? So there's 10 choices for this guy. Okay? She wants the 500 now. So she has, oops, that's a 1. It's a 1, right?
It only has 3 choices.
She have a choice of data plan or not?
Yeah.
2, but she only has what?
3 choices for color.
3 choices for the color. So how many is that? 6. Add those all together. 26. So she has 26 choices. Okay, the number one thing that you need to take from this. The number one thing. The blanks represent decisions. The numbers represent options. When you find those number of ways, you multiply them. When you have different cases, you add the cases together. So I have my options here, 3 different cases. I add the cases together in order to come up with the correct solution. All right? Have we taken everything into account here?
It says on the book that there's only 21.
There are 21 branches?
Yeah.
Okay, so where's our error then? What did we forget? See, the error actually comes up here. I can't, because of the restrictions that were provided, I can't do it that way. I have to look at each individual model in order to do this. So if she chooses the 300, which she can, what does that narrow down?
She has 5 colors.
She has 5 colors, but she only has
One choice.
one choice for that plan, right? Because there's no plan involved. So the correct answer, 21. So there's 21 choices. So what I have to do is I can't combine and look at individual cases. I either have to do one or the other. So if I look at the 300, the 400, and the 500, and let's look at the branches right now. Does that cover everything? In the 300, do I have 5 colors in the branches? And no plan, so that means I have a total of how many choices? 1 choice there, but 5 total, right? The 400, I can choose a data plan or no data plan, and 5 colors. So there's 10 choices there. The 500, I can choose data plan or no data plan, right? But I only have a choice of 3 colors, therefore I have a choice of 6. So it works out to 21. So looking at them individually, that's the easiest way in which you can solve this question. Look at all your options. You can do it using the fundamental counting principle, or you can draw your tree diagram to do it. Okay, so far? I'm going to share another example with you. Okay, this one's not in the book. All right, so I'll come back to example 2 in the book. I have 5 digits. This is what this is leading up to. I have 5 digits. I want a 3-digit house number. Okay, so I want a 3-digit house number. I want, with no restrictions, I want to find out how many choices or how many ways can I get a 5-digit number, or a 3-digit number, sorry, from 5 digits. Can't use the 5 digits, can only use each digit 1 time. How many choices do I have? So I have 3 numbers for a house number, which means I have 3 decisions to make. So in the first blank, how many choices of numbers do I have? 5. In the second blank, 4, and then 3. So how many ways can I choose a 3-digit number from 5 digits then? There's 60 ways in which I can do this.
Would you want times the 5 to the exponent of 3? Or that's saying that you can use them over again.
That's right. That's
If you're only for law combinations, you times by the exponent of the numbers. Right?
Yes. Yeah. Okay, so Brandon's question was, why can't I go 5 to the power of 3? That's because I can't repeat my digits. If I could repeat my digits, it'd be 5 by 5 by 5, but I can't. Okay, this is a house number, so think about it. You're putting actual individual numbers on the house. All right, how many ways can I do this if I needed my house number to be an even number? So I've now put a restriction on it.
So then you have 2. No, you only have 2.
All right, so which decision does my restriction affect?
You can't have three numbers because there's a.
Okay, but which blank?
Last one?
The last one. The last one we're saying
Zero.
has to be an even number,
Make the whole number even.
right? So how many choices do I have from even digits?
2.
2. Okay. So I always start with my restricted value first. Now I look at the first blank. How many choices do I have now? 4. Because I've already selected an even number for that last blank. Right? Then how many do I have here? 3. So how many ways can I get an even number? 24 ways. How many ways can I get an odd number? If I want that last house to be an odd number, how many ways is it?
36.
You
Oh,
see?
yeah, never mind, there's 3. Never
Well,
mind.
times
Yeah.
3.
I understand.
All right. Think about this. There's 60 ways in which I can pick a 3-digit number. If 24 of those ways are even, how many odd ones do I have? 36. Right? So I would have 36 ways. So if I was doing it using my process here, how many odd digits do I have to choose from? 3. That leaves me with how many to choose from here? 4, 3, which makes 36 ways. So both methods is fine to get to that 36. Okay? All right, I'm going to increase the difficulty a little bit here for one question, and then I'm going to get back to what we were doing. I want a 3-digit even number greater than 300. 3-digit even number greater than 300. So now I've placed 2 restrictions on this question. Right? I put a restriction on the first and last blank. So, what are some of the things that I have to take into account then?
The first number has to be, there's only 3 of the first number, 2%. 3, 4, and 5 are greater than 300.
Right?
And then the last number has to be 2 because it's not even.
Right. Okay. So, the first blank, we know that it has to be a 3 or 4 or 5 here, right? The last blank, because it has to be even, is either a 2 or a 4. So this is going to present a bit of an issue because if I pick the 4 for the first, it changes what happens on the last, correct? Or if I pick the 4 on the last, it changes what happens on the first. So the best thing to do now is to look at the cases involved. Because there's only 2 cases for this last guy here, either it's a 2 or a 4, let's look at those individually. So let's make this a 2. Now, the squiggly brackets, when they ask you on the exam, and they will, they'll say, explain your answer on the exam. By placing brackets, these squiggly brackets on the bottom, that's explaining what you're doing. All right? Otherwise, you have to actually write it out in words what you're doing. So by placing those down. So if I have a 2 here, how many choices do I have? Well, I just have 1. How many choices do I have in the first value now? I have a choice of 3. It can be a 3, a 4, or a 5, correct? How many choices do I have for this last number then? 3? I picked the 2. I picked one of these 2. Now I'm down to 3 numbers. So there's 9 ways in which the last number is a 2 and the first number is 3 or greater. So now I got to look at my second case in which the last number was a 4. So that's a 1. So now, what are my options here? There's 2 options, a 3 or a 5, isn't there? I picked one of those. I picked that. How many choices do I have here? 3. 6. Add them together. 15 ways.
So what's the middle one? What does that represent?
It's just any of the digits. Okay, so give me an example of a 3-digit number, 122.
Okay,
Or
yeah,
123, sorry, because I can't, right? So that's the middle digit. All right? So the fundamental counting principle just says put blanks down for the number of decisions you have to make, and then write the numbers of options in the blanks above, and then you multiply. All of that reading that I did there, at the top, if one task can be performed in A ways and another task can be performed in B ways, and it's A times B. That's exactly what this is. You take A times B times C. Okay? Let's look at example 2. From a standard deck of cards, how many possibilities are there for drawing a 2 or a face card? Okay, so there's a lot of card questions in here for those of you that hopefully everybody has played some sort of card game. I know in the past there has not been. Okay,
Quite a lot of
how many?
card games.
So I want the number of 2s or face cards in a deck. So just a second. That means I want the number of 2 plus the number of face cards minus the number of 2s and face cards.
Jack, Queen,
Or a joker, you know, spicy.
Jack, Queen, and King.
The one whose face is on.
All right. How many 2s are there in a deck?
4.
It's 4.
Yeah,
How many face cards are in a deck?
12.
12.
I don't even know how many cards. I didn't know that.
52.
Never mind face cards.
How many 2s are face cards?
None.
None. It's a disjoint set, right? They're mutually exclusive from each other. So the answer to the question is the number of 2s or the number of face cards is 16 cards. Okay. How about a spade or a queen?
Oh,
Number of spades or queens. So how many spades are in a deck? 13 spades. Each suit has 13, yeah. How many queens are in the deck?
4.
4. How many queens of spades are there?
1.
There's 1. So I have to subtract it. Number of queens, no, sorry, number of spades plus number of queens minus the number of queens of spades. Again, 16.
so what happens if I don't know that?
And you need to start learning about cards.
I'm not eating though. That's a retirement thing. I play Uno. I play cards.
Okay?
I have like a sheet where it tells us all this.
Can I just bring a deck of cards?
Yeah, I'll just like that out.
I would go home tonight and find out because you do need to know about cards.
Yeah.
So I'm supposed to study cards for math.
Yes.
So,
All right. One last thing to show you. Go to page 94. 94. The number of permutations or ordered arrangements in a set of n different objects is given as expression n factorial. So this is brand new to you. You haven't seen this notation before, so I'm going to explain it to you. 4 factorial. This 4 exclamation mark. What it represents is 4 times 3 times 2 times 1. That's what this thing means. You take 4, whatever the number is, and you multiply it by every number below it. Now, grab your calculators for a second. The graphing ones work with the graphing ones to begin with. You're looking for this button. You have to go into math and go across to permutation, or sorry, to probability. It should be the 4th one down, I think.
I know. But like when you practice the probability and then scroll over probability.
Your probability.
And then go down.
This
And
is-
then down forward. And then it's good.
Okay. Did everybody find it on the graphing calculator?
This is how.
No, not yet.
Go hit the math button, go across to the PRB, and go down to the fourth one.
Oh, I see.
To the rand? Is that what's supposed to be?
Push enter.
On the fourth one,
Yeah, I'm on the fourth one. Push enter.
yes. Did you get the exclamation mark?
Yep.
Okay.
Gotcha.
So, if you put in this number, put this in, 7 factorial, so use your calculator and find out what 7 factorial is. So you put 7 in first, and then you find your factor.
Seven.
Then you find your,
You put 7 in first?
yes,
Woo!
okay? Everybody get this? You may not get it.
I'm just looking, where would you find the external button?
Oh.
Hit the math button,
Just did that.
go across the PRB, and then down to the fourth one.
Thank you.
Okay, does everybody find that factorial button? Anybody not get it? Girl, stop talking. Did anybody not get it? Okay,
7.
now what's the importance of this? If you were to take the example I used earlier, except this time instead of a 3-digit number, I want a 5-digit number. So I want a 5-digit number. So how many blanks do I have to put down? 5. 1, 2, 3, 4, and 5. And what goes in the first one? So I have that right there. 5, 4, 3, 2, 1. You can multiply that on your calculator, or you could just put in 5 factorial. And that would give it to you. Okay? So 120. Now, this is the part that gets everybody. So you want to do your best to watch and see what happens here. If I have n factorial, so let's look at the 5 factorial for instance. I take the 5 and I multiply it by the next number smaller. And then the next number smaller. The next number smaller. So what is 1 smaller than n factorial? How do I show that?
N minus 1.
I just go n minus 1. So I start with n. Started with 5. I took 1 smaller than it by taking n minus 1. And then n minus 2. And then n minus 3. And that goes all the way down until you hit 1. Okay? So if I'm asking you for 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1. Okay? All you do is you take the first number, which is n, times it by the next one smaller, 2 smaller, 3 smaller, 4 smaller, all the way until you get to 1. Everybody got that? 8 times 7 factorial. Not on your calculators. Write it in factorial notation. What is 8 times 7 factorial? I don't want it. I want it in factorial notation instead. It's not something you can answer on your calculator.
Is it 8 bracket 7 times 6 times 5 times 4 times 5 times?
So what is 8 times 7 times 6 times 5 times 4 times 3 times 10 times 1?
It's 7 factorial.
8 factorial.
Oh,
Oh yeah.
that makes sense.
It's good.
Oh.
Yeah, 8 times 7 times 6 times 8 factorial.
Because you would just
Is
times
that
it by
7
8.
factorial is 7 times 6 times 5 times 4 times 3 times 2.
8 times that is 8.
If you expanded this out, you get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 8 factorial. Okay, by multiplying it by 1 more than that, it just changes it to 8 factorial. Okay. Let's look at the example 1 there, and then I'm done. Example 1, 6-digit code number uses the digits 1 through 6 exactly once. The first digit of the code number is 3 and the last digit is 2. How many possibilities are there for the code number? Okay, so how many decisions do I have to make?
4, 3, 4.
I still have to include the 2. I still have to include the first 2 because it's a 6-digit number. But it's specified. The first digit has to be a what? A 3, right? So that's one choice, correct? This digit here has to be a 2, so that's one choice. So now how many choices do I have in that blank? 4, 3, 2, 1, which is the same as, or 4 factorial.
Yeah.
You're right. Okay? So sometimes they'll ask you to write it in factorial notation, sometimes they'll actually ask you to write out what the answer is. So in this case it's 42. Oh, sorry, 24.
24.
Dyslexic. Okay. I want to look at the first A value of that example 2. The reason I did this 8 factorial trick was exactly for this right here.
We did this last year. The one that we all failed.
Okay. So I have n plus 3 times n plus 2 factorial over n plus 1 factorial. Now, the first thing I want you to establish is which value is larger, the top one or the bottom one? The top one? Okay? So, if the top one is larger and I expand it out, I should be able to get the exact same thing that I get on the bottom at some point. So here's what I'm going to do. I have n plus 3. How do I write out n plus 2 by expanding it? N plus 2 factorial. So I've got n plus 2. What's the next number?
N plus 1.
N plus 1. And then? It would be n, right? And then it would be n minus 1. I'm just subtracting 1 off of each of these, right? That's all I'm doing. So, what's that?
Why would you stop at 0?
I've got n plus 0.
Okay, yeah,
Which is still n.
Subtracts 1 plus n plus 1. So it's just that.
okay. Yeah, I know that.
Subtract 1 from here, so 1 subtract 1.
Yeah, I know, but why would you go n minus?
Well, because it's smaller than that. And then I can keep going. I don't need to. I should have stopped right here. Because now I have the same on the top and the bottom, and those cancel. So what is this simplified then?
N plus 3.
N plus 3 times n plus 2. All I'm doing is subtracting 1 off of each of the values to get to the next value. No, my larger value is on top. That's why I have stuff left on top. What's that? In some cases. If you're solving for something, yes. Plus 5 and plus 6. Right? Okay, so this is just a simplified version right here of what that is. Okay? Brennan's question was, do I have to FOIL this? The answer is no, because I'm asking you to simplify it. But if you look at the B part of this, it has it equal to 30. So now what am I left with? N plus 3 times n added 2 equals 30. All right, so we're gonna look at this in a logical sense, and we're gonna find a solution for it that way, and then I'm gonna show you how to do it algebraically, which is what you'd be required to do. What is this saying? N plus 3 times n plus 2 equals 30. What am I looking for? What's that? N is equal to a certain number. How would I find what that number is? Yeah, but I don't want to do that. I don't want to do the algebra part of it right now. What is it asking you for? Somebody give me the answer.
Looking for n.
What is n? Give it to me right now. 3 plus 3 is what?
3 plus 3 is 6.
And then 3 plus 2 is 3 plus
5.
5
5.
times 5 is 30.
Right. There's your answer. This is asking you to find two consecutive numbers that you multiply to give you 30. What two numbers are consecutive at times to give you 30? 5 and 6. So what does n have to be? It has to be 3. Right? That's it. Like, that's all there was to it. You can do it that way. The way to do it is to FOIL this out. So n times n is n squared. 3n plus 2n is 5n. 3 times 2 is 6. Get it equal to 0. You guys need to start brushing up on this because there's going to be a lot of
You
this.
didn't equal it to 0.
Is it negative? That's negative 8.
He was doing it.
So now I need to factor that.
Oh, shucks.
N and n. Factors of 24, negative 24.
3, positive 8.
It would be plus 8 and negative 3, like that. N is equal to negative 8 and 3. When you are doing factorials, you cannot have a negative value. What is the answer to the question? N is equal to 3. We did that.
So if it's negative, you just take it out.
Yeah. Because it goes to 1 and that's it.
I actually like this.
This
I
is
rather
gonna be a stupid question because I forget factoring, but what I did the first time was I put 6 on the other side, so I put n squared plus 5 and it's equal to 24.
You need to negative that.
And then I figured out on that way. That's wrong. So I got it as equal 0.8.
Okay. You have to finish 4.1 for tomorrow. There's only 9 questions in there. They're not very long. And you can start on 4.2 as well. 4.2 is not long either. It's only 4 questions. So let's get that done.
I will be here next week, so.
All right.
Three times with the math, that's what I do.